Hi everybody, I am Francesco Ragusa from University of Catania, and today I am going to present StillFast, an end-to-end approach for short-term object interaction anticipation. In this paper, we address the problem of short-term object interaction anticipation. Given a video V and a timestamp t, models can process the video up to time t and are required to output a set of future object interaction prediction which will happen after a time interval delta. Each prediction consists in a bounding box localizing the future interacted object, a noun label describing the class of the detected object, a verb label describing the interaction which will take place, a real number indicating the time contact, so the time in seconds between the current timestamp and the beginning of the interaction, and a confidence score used to rank future interaction from evaluation. Previous works addressed this task. The baseline proposed with the Ego4D challenge consists of two components: a faster CNN object detector to detect next active object in the last frames of the input video, and a SlowFast action recognition model to attach each bounding box a verb and a time to contact prediction. The two models are trained independently. In contrast, we proposed an approach that processes two inputs simultaneously and can be trained end-to-end in a single stage, which increases training speed and allows to better optimize the feature extraction process. Given an input video V and a timestamp t, the proposed model takes as input an high-resolution frame and a low-resolution video. To process the input image and video simultaneously, the proposed model comprises a two-branch backbone. A 2D CNN, the still branch, processes the high-resolution frame and produces a stack of 2D features at different spatial resolution, and a 3D CNN, the fast branch, processes the video and outputs a stack of 3D features. We perform mid-level feature fusion by combining the 2D and the 3D feature stacks with a combined feature pyramid layer. The resulting feature map is fed to a standard feature pyramid layer to obtain the final feature pyramid. Then, the obtained combined feature pyramid is fed to our head. A region proposal network predicts region proposals from the feature pyramid. A row-align layer is used to extract local features from the region proposals. We enrich these local features with global representations of the scene, which we concatenate to each local feature extracted from the region proposals. The concatenated features are passed through a fusion network. The resulting representations are summed to the original local features through a residual connection. These fused local global representations are used to predict noun and verb probability distribution and time to contact using linear layers. We performed experiments on the large-scale egocentric dataset Ego4D. We considered both the initial version of the dataset, denoted as V1, and the recently released update of the dataset, denoted as V2. We focused on the subset of the Ego4D dataset which has been explicitly labeled for the short-term object interaction anticipation task. Version V1 of this dataset consists in 120 hours of annotated clips, annotated with a taxonomy of 87 noun and 74 verb classes. Version V2 consists in 243 hours of annotated clips, annotated with a taxonomy of 128 noun and 81 verb classes. We evaluated methods with different top 5 mean average precision measures: noun, noun plus verb, noun plus time to contact, and overall. We compared our method with respect to different approaches which addressed the considered problem. The proposed method improves over the faster RCNN baseline by significant margins in the version 1 validation set on verb-related metrics. This result suggests that the ability of the proposed approach to process images and video with a unified backbone is beneficial for the performance. On the downside, the proposed StillFast approach achieves worse performance on nouns. This seems to be mitigated when more training data is available. Indeed, when training on version 2, StillFast consistently outperforms other approaches. The advantages of StillFast are more evident in the test set, which suggests better generalization of the proposed approach. Non-top 5 mean average precision results are still lower but closer to the ones of faster CNN baselines. Moreover, StillFast still outperforms intern video with respect to noun plus verb and overall top 5 mean average precision, despite being based on less advanced components. StillFast relies on a faster CNN object detector and a X3D video backbone, while intern video relies on Dino and on video masked autoencoder. If we consider that V1 and V2 share the same test set, StillFast jumps from 3.49 of version 1 to 5.12 of version 2 overall mean average precision by merely adding more training data, which suggests that the proposed approach can scale in the presence of a larger dataset. Here, we report two success examples where the proposed model detects the next active object and predicts the verb and the time to contact, which are shown in green, respect the ground truth, which is shown in red. And here we report two failure examples. The model struggles with uncertain future action, put cement versus mold cement, and unusual actions, clean book versus put book. We further investigate other aspects of the proposed StillFast architectures, including the verb-noun prediction trade-off introduced by the prediction head and the contribution of different architectural choices to the overall performance. The tables reports validation result of experiments performed on the version 1 of the Ego4D dataset. Our method is ranked first in the public leaderboard of the Ego4D Short-Term Object Interaction Anticipation Challenge 2022, and it is the official baseline for the 2023 one. The leaderboard shows that there is a method which outperforms our StillFast model with a small margin considering the overall mean average precision. Thanks for the attention.